today's all about networks. I'm going to talk about why we've set out to do what we're doing as far as technology is concerned inside our business, and how we're doing it. I'm going to talk about some of the challenges that we see, and then the fun stuff towards the end. I've got a whole bunch of videos. Everybody loves the videos, so you've got to go through me talking before we get to the videos. That's your penance. You just stick with it. Now, we do have a Rio Tinto lawyer in the back. I've now said it, so you can calm down. You can calm down. It's over now. Blood pressure down. So that basically says you can't believe anything that I say. Lawyers do that, so nothing that we can do. Why? Mining is actually not known as the greatest technology business, if you think about it, in the public. If you look at the surveys, that's changing a bit. It's probably changed over the last 6-7 years, certainly with the way that we've been pushing. So why would a mining company take positions in institutions like Imperial College? It's 5 institutions at the moment. Watch the press on Monday. There's going to be a 6th that's added. It's here in the UK. It'll make more sense Monday. I can't say who it is. Why are we doing it? Ultimately, all of these good things that come out of research and development make life better, they make your operation better, but you also want to make more money. At the end of the day, you shouldn't be afraid of that. There's a good commercial reason to do what we're doing. Rio Tinto, I could spend a good half hour with the boring corporate slides on who we are, what we are, and where we are, but you only get one slide, so you should be grateful for that. This fella here, I can't pronounce his name. He was the king of the Tarsians, and he ruled around 600 BC. And why is he important? Well, he was important because of this deposit. That's Red River, Rio Tinto in Spain. That thing has been mined by humanity for at least 2,000 years before Christ. Probably further, but it's difficult to tell in those mists. These are very important objects in the history of humanity. They attract great attention. In history, they've attracted wars. People have fought over these objects. Why? Because they provide the minerals that society needs if it's going to progress. Without these things existing, you don't have an advanced industrial society. Minerals from that deposit supported the Roman Empire. Minerals from that deposit in the 1200s were found flowing up and down the Silk Road that the Mongolians opened up and made a major trade route. This gentleman here was the founder of Rio Tinto, a chap called Hugh Matheson, and he, with some entrepreneurs, bought from the Spanish government in 1873 Red River, this thing. The general feeling at the time when we bought it was that there was nothing left to mine. Kind of hang on to that thinking, that there was nothing left to mine, that it had been mined out. Well, Matheson brought a whole bunch of contemporary technologies to Red River, to Rio Tinto, and that became the largest copper mine in the world, and I think it held that position for 20 odd years, and we sold out of it, I believe it was the 50s or the 60s. So they are valuable objects. The minerals are required by society. Empires are built upon these things. They're required to fuel progress. And out of that start, and there's another link I'll talk about later on, we end up with this business here. The dots are where we operate. We operate in most places, in a lot of places, and we operate across a lot of commodities. It's still the same theory, still the same approach, that you want to exploit the best mineral deposits you can, and you're feeding them into the societies as they advance. I'm going to leave you with a bit of a conundrum, because I'm not going to answer the question that I'm going to pose, is how do you link a president, 1556, beer, and Imperial College? And beer is really important if you come to university. That chap there was another person that was important in starting our business. It's Herbert Hoover. President Hoover in 1905 was in Australia, and he teamed up with some people who had some new technology that came out of the beer industry, so connections, and they went to Broken Hill and they recovered minerals from the waste piles in Broken Hill. He got rich. He created a company called the Zinc Corporation that fused with the Rio Tinto Corporation in the 60s, created Rio Tinto Zinc, and that's why I'm sitting here today. There is a connection. He also, in his spare time, and I don't know why this guy got the time, with his wife, he took a manuscript which was the first academic manuscript on mining called De Re Metallica, which was published in 1556, and he translated it from the Latin to the English. It's a magnificent piece of work. There is a connection with Imperial College, and it's to do with that rather space Star Trek-y thing on the bottom right-hand side, but we're going to cover that later. We'll circle round to that. That's why you do it. All the good things that I've described. Technology has to move us forward. Technology always moves. In my organization, it says, can we take a measured, risk-based position and get in front of the technology curve and bring new technologies in quicker than our competitors and advance ourselves? We want those benefits, but we are capitalists. We make no bones about it. We actually want to make more money. So we want to bring the technologies in earlier. We want to bring them in. We want to make the organization smarter, faster, and we also want to make it more efficient. Why do you do it? Now, these numbers get quite staggering. There's only one chart. I'm in Imperial. I'm only going to show you one chart, but I'm going to show lots of pictures. So in about over 250 years, we went from an agrarian background through to today. That's Manhattan. 250 years. Over that 250 years, we moved about 2 to 2.5 billion people from the underdeveloped to the developed stage. And I'll describe those and I'll give you some definitions. 2 to 2.5 billion. The next 25 years, we're going to move about the same people up that list. That's the acceleration. I spend a lot of time in China. I spend a lot of time in India. I've got an office in India. So, without minerals, you don't do that. That's very mineral intensive. This is a mineral intensive city. Probably the ore body, I'm guessing that the ore bodies that built London are long exhausted. The ore bodies that are building this thing, they're coming from the new frontiers, from Australia, from South America, from Mongolia now. So this is a huge task. That is an enormous task. It took us that time. We've got to do about the same in about 1/10 of the time. That's the pressure that's on my industry. My industry got very exciting in about 1999. I joined a business called Hammersley Iron. It's a division of Rio Tinto. I joined them when I was here working in London, and we had a record year. We shipped 35 million tons of iron ore. In fact, the company gave us all a crate of beer. It is an Australian company. They do things like that. Today, we announced the expansion of that facility to 360 million tons a year of shippable product. It is just not the same business. As China came in and started demanding, as she was going up her industrialization curve, the industry went very, very hot. And there's more to come. Let's look at some of the drivers. The drivers are underpinned by some challenges. Before we get to the good stuff, which is demand, I'm not talking about peak minerals. Can we just we'll calm down. There's no peak minerals. There's plenty of minerals around the place. Ultimately, if you give me free power, we'll mine it out of the sea. It's a power situation that you're dealing with. But look at what the planet is telling us. When we started the Industrial Revolution, we're pulling copper out of the ground, and you can find it here in the UK, at 17%. 17%. Yeah, some of it is even better than that. By the end of this decade, the average feed into the world's concentrators is below 1%. Okay? And then, once you get below 1%, the graphs are not easy to read. Look what's starting to happen. Energy consumption, if we continue using the same systems that we've used in human history, we are using fundamentally the same systems that we use when we're in caves, which is we break rocks by bashing them together and putting them into compression. Energy consumption starts whipping away exponentially. We have to fix this stuff. We have to fix it. We're not adding to the inventories of new ore bodies. There's plenty of ore out there. The grades are declining. This story plays itself through in many of the other minerals. Some like coal, etc., they're a different game. But these are the main power minerals that will build these places, the non-energy dependent minerals. So, it's the only graph that you get. I'm sorry to disappoint Imperial. Developed status is anybody beyond this number. $20,000 GDP per capita, and this is 2011. So what's up here? That says that if you're rich, and everybody in this room is rich, we all live in very rich societies. We're here. We're very, very fortunate societies. We've built our cities. We've got these magnificent places. We're replenishing the demand for minerals by keeping our cities going. Entropy has this way of making things rust. And you're spending per capita $10 on whatever that one is, copper. That's fine. All right. Look at this wave coming through here. That's China. So as China's going through and building her cities and getting the standard of living that they require, they will go through those curves, and from almost a zero base. By the way, the area under these curves is the population. You add up the area under the curve, you get 100% of the population of the planet. They're coming through their peak growth period now. That's why we have to react. And look what's coming behind them. Okay? So there's a kind of moral dilemma here. We'll get to that in the next slide. Just to make it real for you, that's what happens in 25 years. I've seen that happen all the way through China. And it's starting to happen, fits and starts in India. It's not, that economy is not starting to move yet. It will. So in 25 years, you have farmland. 25 years later, you've got that. That's incredibly mineral intensive. And without the minerals, you just don't do it. They're going to get the minerals because it's a free market. And if we can't put enough minerals in the system, the only other react in the system is price. So we have to keep feeding the system to keep the prices in the way that allows for growth and also doesn't impact the Western economies. Kind of a moral dilemma, isn't it, really? By the way, I gave this slide to the politics and globalization group at Jesus College. We had a fantastic philosophical debate just on this slide for about an hour. So you live here in one of these places. That's Rio, the favelas. And you're seeing growth. You're seeing growth. Typically, these people here are consuming about 40 kilograms a year of steel. Probably less, maybe even less than that. To maintain your standard of living after this city is being built, you're consuming 400. That's what you're consuming. So to get these people from there to there, they're going to double, they're going to double, they're going to double. Otherwise, they're condemned to be where they are. This is what's happening all over the place. This is the result of the greatest transmigration of humankind from the rural landscape into an urban landscape. That's what's putting challenges on the system. And the good stuff's gone, so we've got to use technology. Where do we look? I like threes, because I can't remember more than three generally. You look in three places, and there's three things that you look for. And in our industry, you go to the source of the wealth, which is the ore body. You want to recover more from less. Remember that story about the zinc corporation? Herbert Hoover, the reason why he was president, he got very rich. He brought new technology in and recovered minerals from what was a waste stream. We want to find some new ore bodies. We have the exploration guys out there. Process efficiency, robotics, massive systems. Taking what has been disconnected, pretty brutal industry, big systems, big mining equipment, and running them with the same kind of finesse and the same kind of data architecture that say Toyota run their car plants. But these are very big things, and that's a big challenge. We're a lot data richer than say, the car industry. And energy. This is an energy game. Do you remember the curve? The curve on the crushing? That's coming at you, and we've got to fix that. So that's kind of where we go. That's okay, great theory. What do we need to do to tackle this? And also, at the end of the day, what do we need to do to tackle it early for Rio Tinto and make money out of it? That's what the business school is all about. It's about this. It's brain power. It's brain power. How do we mobilize the brain power to get onto these problems? And the problems are problems, but they're also challenges and fantastic opportunities. We got more opportunities than we can poke a stick at. Where do we get the brain power from, and how do we organize ourselves, and how do we access that brain power? That's really the core of my lecture, and a little bit later I'm going to be showing some of the stuff that these systems have thrown out. Well, philosophically, the world is now a really small place. We're networked. You're probably tweeting, or we're all on these things. The world is networked. Traditionally, an organization like mine, when I was given this challenge, would have gone off, would have built a big facility, would have put 1,000 scientists in it. That's exactly what we didn't do. In fact, we run with a very small central core because we know our business. In terms of business, your domain expertise has always got to be your business. Our domain expertise is not massive mathematical modeling that takes place here for and on behalf of Rio Tinto and Imperial College. Our domain expertise is not very advanced flotation or the fundamental science of how rocks unzip. We know we need to know it, but we don't have to build the brain power in-house. Our culture will not support that. These places support that culture. So that's the traditional, and by the way, in the past, I've seen these things rise and fall. Our industry goes on a cycle. Typically when the cycles are up, you'll build these things. Then when the cycles go down, you're going to knock on the door from the chief executive officer, the controllers, and those nice people in HR, and you'll take them apart again. That's what you do. You make it really small. You make it as small as you possibly can. And what's in the middle is domain expertise. What's in the middle is a network switch. It's a network coordinator. It's the ability to manage intellectual property. It's also the ability to manage the legal side of all of this stuff, because we don't do it for the benefit of the wider industry. We're doing this for our shareholders. That's another core competency I've got to have. And then you link with the best suppliers you can find and the best researchers you can find to attack specific problems. What we don't do, and what I'm about to describe is actually an alternate strategy. We don't have people trawling, looking for neat technology, saying, can we use it? We identify the problems. This is, what can't I do today that if I could do tomorrow would fundamentally change my business? That's the thinking model. Articulate the problem, mobilize the network, take it through a stage gate and attack it. But attack it with a vigor that you're actually going to put something into your operations and deliver it, because that's how you make money. So that's our concept of network technology. That's what we built. I was told to do this job. I was first approached in late 2006, 2007, the job became real. 2007, we brought on our robotics. It was the largest non-government grant for robotics outside the military. That was the ACFR in Sydney, which is a robotics group built out of the Oxford group. And then the second one was here at Imperial College, and then we started to build the network. So this, I won't bore you with it. This is kind of how we spread. We've got some key technology partnerships. These centres, we like long-term relationships with universities, typically 5 years or more, and they'll roll. You know, you can't be doing it on a year-by-year basis or project-by-project basis. Everybody's going to get bored of that. And this chart will change because as of Monday, there'll be another one in there, which is quite exciting, and we'll announce it Monday. And just as a snapshot, because we're networking with people, I don't have to carry nearly $500 million of physical equipment inside my business because I can't use it. You know, I have no use for some of this very advanced electron microscopes or the tomographic equipment that Imperial can access, because I can only use it 1% of the time. But I can slave off those systems. I can leverage those systems. And we get all of this kind of stuff that we can access. But it's a good deal on both sides. It has to be a win-win. Long-term commitment. We can support students. We can support PhD programs that you guys want to run. We can support your postdoc programs because they're working on stuff that we're really interested in and we want to get into our operations. So that's a snapshot. We've got about 2,500 years of collective experience on the system. We look at our system. 160 bachelors, 63 masters, about 80 PhDs, and not many technicians. I cannot build that inside Rio Tinto. I would not be allowed. And by the time I'd built it, we'd have missed a cycle. And also, the kind of assets we have on that network don't want to work for a mining company. They shouldn't. That's how networks work. And that's the spread. That's the spread. There's going to be more in the UK. I'm giving a hint after tomorrow. India is our largest development office. We run that out of Pune. So if you cast your eyes down what's in this thing, as the head of innovation, it's just this marvelous set of tools. And we can pick a problem as it's coming, or a challenge, an opportunity to make money, and apply these disciplines to attack that problem. And we can do it over time. And our Pune Center allows us a development platform that can take a lot of the ideas that are coming out here and we can commercialize them to a state where we can get them inside of our business. It's just a marvelous, I could say it's a marvelous way to work. I don't know how you'd put it together in any other way. I'd struggle. Even if they gave me a blank check, I'd struggle to put it together inside my business. So that's the talky stuff. Hope it made sense. Let's just have a bit of fun. And we can go on for, we've got more videos than the BBC these days. We love making videos. We just love it. And remember that object down there? Remember Beer, 1556, the President and Imperial College? It all comes home to roost with that thing. That'll be the last thing I show. So let's have a look at some of the things that the networks managed to pull together. We started working with a company in 2006 on autonomy. You've seen the Google car. We deployed these things into operations in 2008. That thing weighs, when it's full, it weighs 500 ton, which is about the same size of as a A380 at takeoff weight. It's fully autonomous. There's no humans involved in that. The whole of the pit, the whole of those machines are being managed by a central brain, which is optimizing the system. Multiple layers of safety. We actually have to make them do this, otherwise you wear ruts in the road. And it was the first big deployment of autonomy in the field. I'll run it again. I'll give you a few more things. So the heart of the technology is side sensors, forward radars, very high precision GPS, and in the central brain knows where every machine is, and it also knows the full topography of the mine, and the mine changes all the time. So we have people spotting the mine with lasers to update that world. I ran the trials from 98 through to 2010. So we ran them through the GFC. We stayed with that. And now that is in production. And we have 3 mines where all our machines are autonomous. You may ask, why should it look like that? It shouldn't look like that. The only reason why it's built like that, it was built for a person. The next generation won't have cabs in them. I doubt if we'll, in the iron ore operations, I suspect we won't put another man truck in. We'll go to 150. We will have 1 billion tons a year carrying capacity on this system by 2016, 2017. To date, we've moved about 135 million tons, which if you pack it up as a pyramid, it's about twice the height of the Great Pyramid at Cheops. On the back of those things. The other thing is distance. We learned distance wasn't a problem. I talked about it was 1,500 kilometers away from a capital city, 13 mines, 2 rails, 3 ports, power stations. In one hit, we moved the operations 1,500 kilometers away. And this is part of the system. These people are actually operating. They press a button, something happens 1,500 kilometers away. We have overseers we have oversight and management in the pit, but the actual operation takes place 1,500 kilometers away. We learned from this human systems integration was the next level of, we did it quite quickly, but the next level of productivity was bringing in how the human interfaces with the machines, the display, and that technology came from MIT. There's a lady called Missy Cummins, unbelievably good person in the MIT group. So we're getting a lot more efficiency out of that system by optimizing how people relate with it. We're pushing more tons through with the same number of people. It is the largest of its of its kind in the world. And also we do a lot of data fusion, avatar representation. That's the fun stuff. Everybody loves to do that. What's the key issue here? The key issue is that distance doesn't matter. When you take a very deep breath with your major profit-making system, move all your operations into something that's purpose-built, and you wake up 3 months later and say, well, I'm glad I did it, but ooh, it wasn't easy. Distance doesn't matter. It says that brain power and control, you can put it anywhere now. And I'll pick up on that a little bit later. This is the next generation. It was built with all the learnings from the operations center, and it was really cool. MIT and our Indian human systems group actually ran this thing with avatars and human interaction systems before we turned it on. What it does, this doesn't allow operations, but it brings data in real time from very complex systems into one place where experts, graduates from this place, can optimize that part of the process in real time and also use advanced mineral processing models. The JK Institute that you talked about, they've got 1,000 man-years of PhD experience in advanced mineral modeling around concentrators. That is getting mounted into dynamic models in this system, and we're putting the right people in one place. For us, the difference in operating at normal levels of efficiency and peak efficiency is 3 to 4% copper. So this was as the avatars played the roles, and it was really cool doing it. And that's the main screen. And this is as it was built in the facility. So when you're in that room, you're looking at Mongolia, you're looking at the United States, and you're looking at Australia. You're 100 milliseconds behind real time in all of those facilities. You might as well be there. So we don't need, these facilities need PhDs to run them. We don't have to stick them in the Gobi Desert anymore. And I won't know. It is the world's largest touchscreen. It's really cool. It's kind of your Minority Report. And yes, they can get the grand final on there if they want, but never when anybody's around. Inside there, you just press a button. But we don't often broadcast that, but I guess I've just broadcasted that to the world. Sorry, Sam. So that's the data stuff. For the budding entrepreneurs, think of problems. Think of problems. One of the greatest problems in our industry, and it's a big danger and safety drives us, is changing the tires on these things. That tire is 150 psi. It's a lot of energy in it. Okay, we've deflated it. This person in there is on a rattle gun with ears, and we protect them, but you're looking at 110 decibel environment. So with some entrepreneurs and really good engineers, you say, we want to change the world, and this is what was developed. It's really cool. We ran it. It went back for more software programming. It's going onto the line in one of our operations at the end of this year, the early part of next year. And then the next challenge is going to be scale up and industrialization. And that we need a whole new set of skills. We're not going to industrialize it, but this is an opportunity to create an industry. Every mine site in the world changes tires. And if you can get the price right, this is far quicker, and it's also great process control. Every nut is data-based and all that lovely stuff. Wonderful technology, controllable from your iPad. We have a list of about 24 of these things that we can build, we can put into our operations, and there's a great value proposition straight away. There's another one which is a semi-autonomous water loader. So you can bring, if you get your head into that place, what can't you do today that if you could do tomorrow would change your business? You can develop those kind of technologies because the value proposition works. Labor's expensive in our world, and also it's dangerous, and we can't get the people. We just cannot get the people to run these operations. We've got about another 5 minutes. I'm going to finish off with this one. This one I'll probably... We must have people here that are into big data. You know, it's a big buzzword. We've got 2.3 terabytes a minute of data coming back onto our systems on the iron ore operations. that is fantastic, because if you can start to use that information, and we're adding more information as we go through, we can create some really cool stuff. In the 1970s at MIT, there was this work done, what they call battlefield picture compilation. Can you take in from a very entropic environment all the data from all the sources and make sense out of it? The mining business is a bit like that. If we're going to run it the same way as a Toyota car factory, this is what we need to do. We've worked with the ACFR in Sydney. There's a lot of military stuff in this. I'll let the video play. If the sound comes on, we'll be okay. It's the only one with video on it.
Automation is an exciting and productive new area of technology that will deliver a transformational change to Rio Tinto, not seen on this scale before in the mining industry. It will provide us with a competitive advantage by lowering mining costs and differentiating Rio Tinto as a technology leader. Mine automation is much more than just automated equipment. It's an entirely new, holistic and more integrated approach to what we do. The key to maximizing our performance is adding each new piece of data to the big picture immediately, so that we're all looking at the same big picture as it continually and incrementally changes. As our technological capacity increases and hardware systems become capable of taking direction from increasingly sophisticated systems, we're moving closer to the benefits of fully automated mining, where human resources are tasked with operating entire systems rather than a single drill or truck. We're developing a system that can sense, think, and act in real time as it receives a continual flow of data from every piece of plant and equipment on every site. The Rio Tinto Centre for Mine Automation was launched in August 2007. Our 10-year
I have a lot of fun with this stuff.
is to develop a fully autonomous, remotely operated mine to support expansion and enable mining to plan in a more controllable and predictable way. We've developed a blueprint for what the automated mine should look like and the supporting architecture. This is not just a new database or an upgraded piece of software. The mine automation system is an incrementally developed and deployed real-time system, spatially distributed throughout the Rio Tinto operations for maximum security and flexibility. Every piece of plant and equipment, drill rigs, haul trucks, excavators, and dedicated sensors will deliver data to the mine automation system, continually updating information to create the most accurate, most up-to-date common operating picture of the mine. Virtual islands of autonomy will be created, which are responsible for the acquisition of data relevant to their own area of operations. From a drill island, an automated drill rig will require and transmit information about the geology in the drill bench back to a control center automatically. The road island will collect a stream of information about vehicle traffic. An excavation island will control excavators and trucks in the load and haul cycle. The island might send out a sensor vehicle to laser scan the pit to check measurements, or to use its hyperspectral camera to automatically scan a rock face for more up-to-date information about the properties of the ore about to be mined. These virtual islands will collect and share data amongst themselves and amongst other islands distributed throughout the mine and the business. Information is power. The mine automation system is harnessing the immense power of our data-rich operating environment so that we can use it to work more effectively and more profitably than ever before.
To get there, that's a good story of the networks. We'll jump to this. To get there, we needed the professor that left Oxford that set up the ACFR, the Australian Centre for Field Robotics, where he attracted Defence Department, BAE Systems. A lot of that, most of that technology, a lot of the technology comes from Defence, although we're handing some back. And we needed the ability to attract basically 20 postdocs and 20 other professional students to work on this system. I could not do that inside my business. You do it in a center. But what they're working on is directed by us because we know the domain. We know where to look. That's how harmony happens and win-win happens. So back to beer, and it's nearly beer o'clock. Hoover went to, in 1905, went to the Broken Hill Company with some entrepreneurs and brought a technology in from the beer industry. It was flotation. It was very early flotation. And that allowed us to do something, the industry do something that was counterintuitive, which is take heavy metals and make them float. That is really kind of weird at the time. Think about it. It's what we do. That thing there is not here today. It came out of the head of Professor Jan Sillers and that fantastic group that he has working over in the chemical engineering department. Imperial College probably has one of the best flotation groups, fundamental flotation groups in the world. So that's the tie between it all. We talked to Jan, and Jan had built many mathematical models, and we've actually built a whole string of PhDs on this stuff. What he needed was a partner to turn it live, and that's where we came in. And not only could we turn it live, we had the facilities to trial this thing on, but also we had the capacity to do the industrial engineering that a university can't do, and to bring all this stuff together. We won't play the sound. I'll turn the sound off. I'll explain what's happening, and I think we'll call it a day at that. We've got more videos than soft mic, but we want to talk a little bit. So this is straight out of Imperial College. They're flotation cells. So you take this mineral, you make it float. I'll stand here for you. They're the flotation cells. It comes over the top, and it's all to do with the amount of air that you're putting in the system. Now, that sounds simple. There's PhDs that are this deep on this system. Inside this very chaotic system, which happens here, he can pick that apart, and we've actually tracked particles in the system. These air bubbles, with the chemical treatment that's around them, attract the sulfides. They float over the top, and that's what we want. We don't want this junk, the red stuff. So, as air goes in, the stuff floats and it comes out of the top. The theory is that the best operational condition is when the maximum area is recovered. I get it. It took me a while, but I get it. The real issue is how do you control that on a massive industrial scale? As volumes move, as concentration moves. So this was all very theoretical work and empirical work done at Imperial. That's saying that one ain't going to float. It's going to collapse. There you go. At the other end of the scale, putting too much air in, and you're blowing the system apart. It's very inefficient. Lightly loaded, bubbles break, loss of efficiency. By the way, this is where the money is made in a copper smelter, in a copper system. I've got to get the system out. Jan's work opened up the theoretical understanding of how to be here. Don't underestimate how hard that was. So that's what it opened up. We took it. We've worked with him. We've worked with industrial engineers. We've worked with our facility in Pune. And it's now live and operational on one of our operations in the US. It goes to Mongolia shortly, and we'll get an extra about 2% copper out of this thing. So that's the link, the network, the stuff that happens in universities, the thinking, the inability, because it stays trapped in there, our ability to see a challenge, our ability to put a network together, because it's not just the network between Rio Tinto and this group, it's the industrial network that has to come in. It's the legal network, it's the intellectual property system, so everybody wins. And then it's the ability to push it forward and test it. I think it took us about 4 or 5 years to run that program through. There's a heap of those things, and that brings me just to the last slide. If we look at what's going to happen to our industry, and is already happening, world's largest operation centre, 13 mines, I think 6 power stations, 2 railways, 3 ports, came in within a few years. These excellent centres coming up, autonomy and robotics, these systems coming out of Jan's world. It's very complex. At the end of the day, we have to have the right humans running our world, because humans run companies. Humans run companies. Machines don't run companies. And the humans will change. Our industry is now starting to attract a whole raft of different people because they see this is the world that they want to work in. I put an advert out in the height of the height of the demand for people in Australia, and it says, please come and work. Do you want to come and work on Mine of the Future? We only did it on the internet. We couldn't get people to work for our operations. I had 2,500 people want to work for me, a lot of them from the competitors. So, take this in note, but think about that. What are the business models? What are the people? How's all this going to work going forward? That's all I've got. Thank you very much.
Let me just pick one, just to pick up on the people. And I get the autonomy, and we can fly drones over Afghanistan.
We're actually flying them inside the concentrators.
from Texas. But most of us in here also know that deployment of technology in the field can be a little bit different from the simulation in the lab.
Yep.
And we know that your operations now are in difficult to get to places at Pilbara, wherever it is, and people probably don't want to go and work there for too long. So can we just open that up a little bit and just articulate the distance between those wonderful simulations and the stuff we're doing here in West London, and the difficulties and the tricks of deployment when you're putting it in the field? Because I think there is, and the human interactions that go with the machine
Sure.
and the autonomy.
Sure. That's a lecture on its own. And it's not just the autonomy, it's all the other technologies. First of all, like everybody else in my kind of business, you have to have stage gates. So we start off with idea generation, and you'll want thousands of those. Then proof of concept. The work here would have started as a proof of concept. You're spending modest amounts of money to say, look, does this thing make sense? And then it has to pass some very rigorous tests before it goes to pilot. It'll generally get tested in a friendly place for pilot. And then it has to go to demonstration. By the way, as you go through the stage gates, the technical uncertainty falls, but the financial exposure goes up. To run that test on the trucks and the drills was $100 million. That's kind of, you've got to look the chairman in the eye and say, trust me, but you don't go that far. There's a lot of measurements around this thing. Then when you go from pilot, you go to demonstration. Then from demonstration to deployment. As you go further down that chain, the integration with operations increases almost exponentially. Towards the end, when you're in deployment, it is operations that are running it. But when you're in pilot and really in proof of concept, you have to have a line of sight on how you're going to deploy this thing around the world. So the human discussion, the technology over distance discussion, the robustness discussion really starts quite early. But it's almost like a relay race. As you're moving into the pilot stage, into the demonstration stage, it's 50% operations, 50% me. When you're into deployment, it's 20% me, 80% operations. And without a line of sight on how you're going to integrate these technologies into the current operating environment and how you're going to support them around the world, they will never get liberated. The majority of my work is in that area, to be honest with you. And it's the expensive end of the business.
You spoke a lot about how you're mechanising and automating the production side of the industry and how grades are declining slowly over time. What is Rio Tinto doing on the other side of the business, the exploration side, which is still very labour intensive and still quite primitive in comparison to how the oil industry is operating? How are Rio Tinto plugging things into new geophysics and new things like that?
I haven't got the video on this one. Well, firstly, wave-field tomography, which was used in the oil business to better object what's down there. We've been working with Imperial trying to bring that into our industry. It's not really been done. But it's a long and winding road, and I just manage this thing. We've been at it for about 30 years, but that's a long story. We want a 1 ETVOS gravity gradiometer. 1 ETVOS. And for anybody who doesn't know that, this is weird science. This is superconductivity. The instrument runs at liquid helium, so 4 degrees Kelvin. We measure deflections. We've talked about it publicly. You can find it on the website.
I've seen a few stuff.
Yeah, if the thing sees an ore body, it twitches. The twitch at the end is 1/1000th of the diameter of a hydrogen atom. Go there. I'm a chemical engineer. I don't understand this stuff. I don't understand the maths. But that's a long-term. If you can crack it, boy, you then open up different. So we use every geological exploration tool available. We try and bring some stuff in from the oil business, and our geo guys are really good. And we're willing to take a punt to say if we could get to 1 ETVOS, there are industrial systems out there that are orders of magnitude more, then we can unlock something interesting. And that work was done, that work's been on for a long time. Looking good. But this is every bit of that thing we've had to build. If you work in helium temperatures, you're down in quantum physics.
I'm interested in finding out about how advanced are the technologies which accelerate environmental recovery, say after iron ore extraction?
Okay, you have an environment. We have environmental programs all the time. That whole environmental field is basically a whole division. But it's difficult to say it transfers from iron ore to other industries. If we think about, let's think about mineral sands. Mineral sands in Madagascar, we basically peel back the forest, we go through with dredgers, we take the mineral sands out, we put back the sand, we put back the soil, but the technologies there are all to do with the bugs. It's not you can see regrowth. Regrowth will kind of look good, but our entomologists don't let us off the leash until the substructure of the soil and the bugs have come back to the same level as it was when we went through. With the iron ore business, there's a couple of other plays in iron ore. We are now going below water table. So we manage around, we revegetate, but we're now going below water table. The watershed in the Pilbara is constantly recharged from cyclonic lows. So we're pulling out of our operations enough water to basically supply a town of 1.5 to 2 million people. That water is now being used in the desert to grow crops. And that system is going back in to feed the agriculture. So it's horses for courses. You have to look at each one. But we have whole environmental divisions that will look at the mine rehabilitation plan and the environmental control throughout the life cycle. When you get, I'm thinking of one of the cleanups that we had to do in the US. It would involve bioscience, putting biology down there.
I'm asking because I'm from Brazil, where from Belo Horizonte, huge iron ore there. But as you fly, you can't see. There's no recovery going on whatsoever. That's why I'm asking you, because I think authorities would be interested.
You got to rehabilitate.
Yeah.
Over time, these things will rehabilitate.
It just got time
frames, isn't it?
That's correct. Over time, it will rehabilitate.
You can't look at things in 20-minute slices in 20 years.
To rehabilitate, say the Madagascar iron ore, Madagascar mineral sands operations, it's about 25 years. It will look good after, say, 5 or 6. But to get it back to what it was before we went through, but you can do that because the volumes that we're pulling out are relatively small. It's 20 to 25 years before you get the bugs. The entomologists are happy.
I come from Chile as well.
Yeah.
And the thing is, my question is how to hedge the innovation. Because I was working in some cluster projects over there in Chile.
Corfu.
Yeah. Very good ideas with the national suppliers. They have very good initiatives in order to increase recovery or create the bacteria as well. But sometimes in times that you need to reduce the cost, I was working in BHP. You need to, some of these projects were stopped. And you spend a lot of time, 1-2 years, creating the environment for this innovation. And one day you need to stop. And the question finally is how to hedge the innovation until you are going to arrive to maybe some disruptive or breakpoint.
We all wrestle with that. I think the oil business, you can go and look at some real interesting histories there. I think there's a bit of financial engineering required. Typically innovation sits as a, in everywhere, it sits as a line item on the P&L statement. And it's on the cost line item of the P&L statement. I think there's some financial structuring that needs to move it into vehicles where it's an asset on the balance sheet. If it's an asset on the balance sheet and you are valuing that and you're working with the markets to be able to value that risk going forward, and then who owns the vehicles, how you share those vehicles, that's actually a different debate to how much room I'm going to give you on my profit and loss account. I think that's a very philosophical debate. We could probably spend a week here knocking it about with some whiteboards. Maybe we'll do that one day.